Okay, just before we go into our first lesson on systems of equations, I wanted to do a little bit of review of our systems from last year. So, a system of equations, sometimes called simultaneous equations. And the general rule of thumb is the number of variables indicates the minimum number of equations needed to solve for those unknowns or to find a solution. And speaking of the solution represents point or points of intersection if you're graphing. And if you're solving algebraically, the solutions are values that will satisfy all equations. In terms of solving, we've got our three options that we learned last year, and they are graphing. Graphing is really useful to check or when exact values aren't needed, or perhaps you're not asked to show an algebraic solution. So then that's a quick way to get to a solution is through graphing. Other options include substitution, and substitution and elimination are two methods where algebraic solutions are required. And sometimes students ask me, oh, well, if algebraic is going to work for both, do I need to know both methods? And the answer, of course, is yes. It's kind of that idea of efficiency. So just like when solving a quadratic, people say, hey, well, if the quadratic formula is always going to do the trick, why do I need to know how to factor? And of course, it became an efficiency piece as well. Factoring applies itself in so many other areas as well. So knowing both substitution and elimination is important. So substitution is ideal if a variable has a coefficient of positive or -1, meaning that it can be easily isolated. If we don't have a coefficient of 1 or -1, can you still do substitution? Can you still isolate a variable? Of course you can. However, you're making life perhaps a little bit more difficult because you may end up with fractions or decimals that you're having to work through, and that obviously affects our efficiency. Elimination then is a solution to that. So if we don't have a coefficient of plus or -1, then elimination is going to be our algebraic method of choice. And so you're going to pick one of the variables and then multiply one or both equations so the coefficient of that variable is either the same or opposite. And so my preference is always going to be that you select opposite coefficients, and that allows you to add the equations in order to eliminate the variable. You could also use the same coefficient, but then that requires that you subtract the equations. And almost every error that I have ever seen when it comes to system of equations results from people subtracting incorrectly, and that's often when negatives are involved. And of course, to verify or check our solutions, we want to substitute the values into all equations, ideally in their original form, because that's where we may find any of the mistakes. If you're checking it and substituting it into a form where you've kind of cleaned things up, then that might actually not catch an error if you were to have made an error. Okay, so let's just do a couple of quick just review questions on solving linear systems of equations. And so, of course, I'd like us to solve algebraically and to then verify. So here's our first example. We've got our two equations, 2x minus 5y equals -7, and 1/2 x minus y equals 3. So at this point, I could go ahead and first, actually, sorry, I'm just going to number these equations. And so it helps from a communication standpoint, you recognize which equations I'm referring to. to, and so you may choose to include that in your notation as well, so that anybody looking at your work, not just me, can actually follow where you're going. So equation 2 already has the y coefficient as -1, so I could go ahead and choose to isolate that y. However, you can see that I've got a coefficient of 1/2, and the whole idea of substitution ideally is we're avoiding having fractions in here. Not that 1/2 is difficult to deal with, but let's just show what we can do with this. So I recognize, though, if I was to multiply equation 2 by 2, then my coefficient of x is just 1, and then that makes life a lot easier to substitute. So let's do that then. So we're going to take equation 2 and we're going to multiply it by 2. So that is then multiplying this whole equation, everything by 2. And so new and improved is going to be x minus 2y is equal to 6. And then we'll rearrange it by adding 2y to both sides. So then x is equal to 2y plus 6. So we added 2y to both sides, and so I'm going to just, that's a variation of equation 2, so I'm going to call that 2a then. So now that x is isolated, we're going to substitute 2a. So we'll write sub 2a in equation 1. So then 2 times x, except x is 2y plus 6. So 2 times 2y plus 6 minus 5y is equal to -7. And now we have one equation, one unknown that we can go ahead and solve. So go ahead and hit pause, and then we'll come back with our solution for y. Okay, so we distributed that 2 into our brackets. Whoops. Let's get that working again. Okay, so that 2 was distributed in, so we've got 4y plus 12 minus 5y equals -7, and then cleaned up, collected our like terms, so 4y and -5y is -y plus 12 equals -7. Subtract 12 from each side, so -y equals -19, and we can multiply both sides by -1, so y equals 19. So of course that's not our solution because we're looking for x as well. So now we can sub that into 2a to quickly figure out what our x is. So x is equal to 2 times 19, or 2y, plus 6, so that is 38 plus 6, also known as 44. So just to double check then, so we think x is 44 and y is 19. So we want to go back into our original equations to ensure that that all works. So I'll do that on the side here. So check in equation 1, so 2, our left side is 2 times 44 minus 5 times 19, and that is 88, minus 5 times 19 is 95, so that is -7, and the right side is also -7, so left side equals right side. So far so good. So now we'll check it in our second equation. We're going back to our original, so the left side was 1/2 of x, so 1/2 of 44 minus 19. Half of 44 is 22 minus 19, which is 3, and our right side is also 3, so left side equals right side, and that is good. So then our solution, and we can write it in a couple of ways if you recall. We can use our set brackets, and we can just simply list it and say x equals 44 and y is equal to 19, so that will totally work. Another option is, because for sure, since we've got x and y, then that is also likely going to be a point or an ordered pair on our graph, so then we can show that we have an ordered pair, 44 and 19. And that is our solution set then. Okay, let's take a look at a system of equations that we're going to solve by elimination then. So I'll just change a color here. So example 2. So our equations are, our system is 5a plus 3b equals 3, and that's equation 1. Equation 2 is going to be 3a minus 7b is equal to 81. Okay, so you can see we don't have a coefficient of 1 or negative 1, and so if I was to try to do substitution to isolate either a or b in either of the equations, we're going to end up with some fractions, and that's going to make substitution just a little bit more challenging, not impossible by any means, but just more challenging. When we deal with fractions, that's often where mistakes can happen. So if we can avoid that, we try to avoid those fractions. So then we look at elimination. So we can either aim to get the coefficients for the a's to be the same or opposite, or the b's. And so I'm going to talk through both of them for you. So let's talk about let's work on the a's first. So I've got 5a in equation 1, 3a in equation 2. So a common multiple is 15. So that means that we'll take equation 1 and multiply equation 1 by 3. And so if we multiply equation 1 by 3, our new and improved equation is 15a plus 9b is equal to 9. And similarly, we have equation 2 that we're going to multiply by 5. In which case, new and improved here is 15a minus 35b is equal to 405. And so now that our coefficients are the same, then we are going to subtract these equations. So 15a minus 15a, that's obviously 0. That's a simple one. And this is where things get more challenging when you have the negatives, when you have the larger numbers, say, being what you're subtracting as well. Then that comes challenging because our brain is so busy working on maybe this negative piece. By the time we get to 9 and 405, when our brain sees things stacked, then it instantly wants to add. And that's where the trouble arises. So if you can either maybe change it into, so options maybe, if you're set on doing this, it ends up being the opposite, of course, is to end up adding the opposite. So that's one option to do, okay? Or if you absolutely insist on doing subtraction, if it works, yep, go for it. However, if you find yourself making a lot of errors, I would strongly suggest that you look at maybe multiplying it by -5 so that you have opposites that you can just go ahead and add. Okay, so just providing these cues for our brain helps us to make fewer mistakes. So 15a minus 15a is just going to be 0. 9b minus -35b is then going to be positive 44b. And then 9 minus 405 is going to be then negative 396. And then to solve for b, we'll divide both sides by 44. And so then b is equal to -9. Okay, of course we still need to solve for a, and that comes from the substitution piece. So why don't you just hit pause, solve for a, and then we're going to go through this one again by looking at the opposite. Okay, so sorry, let's just scroll up for a second so you can see that I substituted b equals -9 into the first equation and back into the original. Certainly I could have used one of the other two that had the 15a, but the numbers are smaller. It's going to be easier, especially if I'm trying to do some mental math here. So 5a plus 3b, or 3 times -9 equals 3, and then we just solved for a being equal to 6. So obviously we're going to check our work and go back into those original equations, but I just want to take a moment then to show you what happens if we add instead, and perhaps how much easier I hope you consider this might be. And I'm sure some of you are thinking, oh, it's just the same thing. It really is very similar. However, I have personally seen over the years that students make fewer mistakes if they are adding opposites instead. So choices that we have, so we can certainly look at the a's again, and say multiply the first one by -3 and the second by +5, or the first one by +3, the second one by -5. So those are options. The other idea as well is, since our coefficients for our b's are already opposites, then I don't have to multiply through by a negative. So that might be an idea. So I'll call those equations 1 and 2. So a multiple of 3 and 7 is 21. So I will multiply equation 1 by 7. So if we multiply equation 1 by 7, we've got 35a plus 21b is equal to 21, and then equation 2, I'll multiply that by +3, and we'll get 9a minus 21b is equal to 243. And then we can see that if I add then the two new equations, the b's, +21b, -21b, that instantly ends up being 0b's, essentially canceling out the b. So then now I just have 44a is equal to 264, and you can see that probably would have been better had I lined up my place values as well, and then we divide both sides by 44, and it turns out that a is of course 6, and that shouldn't be any surprise right there. And then we can substitute in either to equation 1 or equation 2 then to solve for b. So since you guys presumably know how to do this already, I'm not going to continue with that piece then. So b we should find is -9, and then of course we're going to check. Okay, so let's get to the actual lesson itself. Okay, so I'll just Okay, so we are on page 501 in your workbooks, and today we're looking at linear quadratic systems. So previously, what we just reviewed was linear systems of equations. So the linear quadratic system is, as it says, in which one of the equations is linear. So it may be in the form y equals mx plus b. It may be in the form of, it might be in a general form instead. The other quadratic is a form y equals ax squared plus bx plus c, and you guys are well familiar with quadratics at this point. So we want to determine values of x and y that satisfy both equations, and therefore we have solved. So here, your first talk of calculus. So if we're looking for shaded regions or shaded areas between the parabola y equals x squared and the line y equals x plus 6, then we need to know those points of intersection right here, and that's where that system comes in really handy. So let's take out our calculators and we'll practice not finding the area. No calculus yet, and we're just going to find those coordinates or points of intersection. So the question, the workbooks actually set this up really nicely for us. Whoops, I'll minimize that again. in that they've already isolated y for us. So that is one point that I forgot to mention when it comes to solving systems using graphing. Obviously, we have to isolate y in order to enter that into our graphing calculators. So in this particular case then, we are, whoops, let's see. Clear. So we need to graph both of these, so it doesn't really matter the order that we're going to graph. So the first one was y equals x squared, and our second graph was y equals x plus 6. So let's go ahead and graph those. And the key piece in this particular case is that we can see both of our intersections on the graph. Obviously, we'll need to adjust our window settings if you can't see both intersections. So in order to figure out those intersection points, you want to consider which ones you're going to find first. So again, we're looking at that calculate menu. So second, trace or calculate, and of course that fifth option is intersect, so you can just arrow down to that or just quickly hit 5 as that fifth option. So first curve, again, just a review on graphing, you can see when I go up down, that goes between y1 and y2, our two graphs, and so this is obviously the most relevant if you've got multiple equations that you're graphing. With two graphs, it's not as big of a deal. What does matter in this case, since we have more than one intersection, is you want to move your cursor, so using the left and right, closer to the intersection that you were looking for. So it doesn't have to be right on it, just closer to this one than to the other one. So first curve is on y1 and it's close to that first intersection on the left, so I'll hit enter. Second, you can notice that they've already put the flashing cursor close to that intersection that I want, so I'll just hit enter. And then it says take a guess, of course, and there's our first intersection, so -2 and 4. So I'll just make note of that first. So -2, 4 is our first intersection. So then for my second intersection, we'll go second trace, calculate the value again, so that that intersection, so that's a fifth one. So you notice my cursor then is back where it was. So this is actually a really big deal because I need to make sure that that cursor is closer to that second intersection point. So we just hold down that arrow key as the cursor moves over and then hit enter, and again it's automatically moved it for us close to that. Yes, and there it is, and it is at 3, 9. Okay, so we've got two solutions, so 3, 9. And so if we are going to do this using substitution or elimination to algebraically determine it, so we've got if y is equal to x squared and y is also equal to x plus 6, then this sets us up perfectly for substitution because y equals this, y equals that, so therefore this equals that. So therefore, x squared equals x plus 6. And so there we have our quadratic, and remembering our different methods to solve a quadratic. Ideally, we will factor if we can, because that is the quick way to do that. If we can't factor, then quadratic formula is probably your next best option unless it's given to you in vertex form. So of course we want to set that to 0, so it makes sense because we'd like our x squared to stay positive, so we'll subtract 6 and subtract x, so then we've got x squared minus x minus 6 is equal to 0, and that is one that's easily factorable. So we've got x minus 3 times x plus 2 equal to 0, in which case either x minus 3 equals 0 and add 3 to both sides, so x is equal to 3, or x plus 2 equals 0, and so subtract 2 from each side and x equals -2. 2. So, of course, these are not the intersection points because those intersection points are ordered pairs. Therefore, there is also a y value. So we need to substitute that back in. And so either one works. We can say y is equal to x plus 6, so 3 plus 6, and therefore y equals 9. And in this case, y is equal to negative 2 plus 6, and y is equal to 4. So with this, it can be, because we've got these 2 points, you can imagine it can get really confusing if you were to write x equals 3 and negative 2 and y equals 9 and 4, which one goes with which. And so that is not how we want to note our solution. It is very important that you write your solution kind of like how we have right here as these 2 ordered pairs. Again, you can use those fancy set brackets to indicate that that is our solution as well. So if we're verifying our points, that we want to satisfy the system, so some people argue, and I agree, that if you've already found your y value using that second equation, y equals x plus 6, then what's the sense in checking it in that one? And I totally get that. If you haven't used the original to find the other values, then you should definitely verify using both original equations. So let's make sure that it works out for that first equation. So left side is equal to, so check in 1. So left side is y, which is 9, and the right side is x squared, or 3 squared, which is also 9. So left side equals right side. In our second equation, or sorry, we need to do that first one again, but with that second one. So for that point negative 2, 4. So then left side is equal to y, which is 4, and the right side is x squared, which is negative 2 squared, also 4. So left side equals right side. So if we had used a modified equation to find it, then we'd actually have 4 verifications essentially that you'd need to do. Okay. And you can see right there. So the solution to the linear quadratic set of equations can be written as x equals 3 and y equals 9, or x equals negative 2 and 4, or as sets of order pairs, so 3, 9, and negative 2, 4. Okay. Let's take a look at investigating the number of solutions. Okay, so in terms of the number of solutions to a linear quadratic system, recognizing, so before we actually do anything, I just want you guys to consider, so if I've got my quadratic right here, and recognizing that a system of equations, then, including a line, then, and our solution is point or points of intersection. So consider, just even, quickly do a sketch on the side. So you've got a quadratic. Where could those lines go so that you could have how many solutions? What are the possibilities, right? And so I think most people recognize that if there's my quadratic, then if I've got my line that's going beneath it, that we could have 0 solutions. If we have it going through the quadratic, then that's obviously going to be 2 solutions. And what other possibilities might you have? And so depending on the slope of our line, could we have 1 solution? Yep, absolutely. Okay, so 1 point of intersection. And are there any other possibilities? And of course, the question that often comes up is, well, does a line have to be straight? Yes, all lines are straight. And even if you consider the lines that you guys are graphing in the form of y equals mx plus b, yes, they are all going to be straight lines that you can draw with your ruler. Okay, so these are the three different possibilities, of course, then 0 solutions, 2 solutions, and 1 solution. And so what I want you guys to consider then is what happens. Obviously visually it's very obvious to us, so what happens when you're trying to solve it algebraically? So if you haven't actually graphed it and seen what happens when you're just solving it, how will you know how many solutions you actually have? And so take a moment and think about that and see if you have an answer for yourself even before we do the work. Okay, so let's take a look at that actual example. So we've got the graph of y equals x squared minus x minus 12 as shown on the grid, and so that's obviously our quadratic. And algebraically determine the point or points of intersection of the line y equals 3x and that parabola. And it also asks us to sketch the line and plot those points of intersection on the graph. So let's do it algebraically, even though I know that you guys can and should be able to graph y equals 3x even without knowing what those solutions might be. So if we have y equals 3x, y equals x squared minus x minus 12. So again, substitution works out brilliantly in this case. So we can then say that 3x is equal to x squared minus x minus 12 because they both equal to y, so of course they equal to each other. And we'll subtract 3x from each side. Then in order to set it to 0, so 0 is equal to x squared minus 4x minus 12, and as a quadratic we know we can factor that, so we've got then x minus 6 and x plus 2. Based on the zero product rule, either x minus 6 equals 0, in which case x is equal to 6, or x plus 2 equals 0, so x equals negative 2. When we substitute those in, because y equals 3x, so y equals 3 times 6, which is then 18. And in the other case, y is equal to 3 times negative 2, which is y equals negative 6. So our points of intersection, and whoops, I've run out of space here, then would be 6 and 18, as well as the negative 2 and negative 6. So I can, if I wanted to graph those, I can do one of two things. Obviously, I could just plot those 2 points on here, 6 and 18 and negative 2 and negative 6, and I only need 2 points to draw my line. At the same time, I want to check by graphing, since x squared minus x minus 12 is already graphed for me. Y equals 3x is super simple, or should be super simple to graph. So if it's in the point form of y equals mx plus b, our y-intercept is obviously the origin, so it goes through the origin, and the slope is positive 3. So rise 3, run 1, rise 3, run 1, rise 3, run 1, and so on. And we obviously hit the mark there. Same thing if we're going down, down 3 and left 1, and we hit the mark as well. So that's just even more confirmation for us on that then. And so you can take your ruler and draw that all the way through our graph, not just stopping at those points of intersection. So that is then y equals 3x. Okay. So repeat for y equals 3x minus 16 and that quadratic. So once again, why don't you hit pause and try working through that solution algebraically as well as graphically, and then we'll come back, hit play again when you're done. Okay, let's take a look. So we've got y equals 3x minus 16, y equals x squared minus x minus 12, y equals this, y equals that, therefore they equal each other. So we've set them equal in our equation right here. And then we've noticed that it's a quadratic, so to solve that quadratic, we'll set it to 0, x squared minus 4x plus 4, factor, and it ended up as a perfect square trinomial, so x minus 2 all squared equals 0. If you wrote x minus 2 times x minus 2 equals 0, that's fine as well. And so then, of course, x equals positive 2, solving for y, that is negative 10. And so when we graph that, we see our y-intercept as negative 16, and we see our slope as positive 3. This was an interesting piece. When you graph, it almost appeared that there were 2 points of intersection, which can't be true because, of course, the quadratic has a slight curve to it, so it's impossible for it to hit at 2 points right there if it's going to be tangent to that. So that's where doing that algebraic work then proves to us the fact that there is only one. And oftentimes, depending on the window settings that you guys select for your calculators, it may not be obvious. Either you're going to be mistakenly thinking that there's only one solution when there are two, or you might think that there's two when there's only one. So just be careful of that, and that algebraic piece serves that purpose for actually checking things out for you. So if you turn to that next page there, it says repeat part A for y equals 3x minus 24. So we can already see graphically, visually, or I hope you can anyways, see that with y-intercept now of negative 24, 1, 2, 3, 4, that this is totally going to miss the mark, and we're going to have 0 solutions then. So I guess, so why is this worth continuing? Some of you might be asking, well, why are we going to continue going through this, the rest of the solution, if we can already see graphically that it's going to have 0 solutions? I think it's important because, as we just said with that red line, it's not always super clear as it is with the screen line right now, this being y equals 3x minus 24. So let's find out what happens when we do that algebraically. So y equals 3x minus 24, y equals also x squared minus x minus 12. I believe that's what that was. And so y equals this, y equals that, so they equal each other. So again, hit pause right now and carry through with that solution. Okay, so we got down to that quadratic simplified trinomial. 0 is equal to x squared minus 4x plus 12. It didn't factor nicely, and so our only choice was then to go into the quadratic formula, because we can't, just because it doesn't factor does not mean there are no solutions. It means there's no rational solution. So we substitute our values into the quadratic formula and then recognize that that radicand, or in this case the discriminant, b squared minus 4ac, ends up being negative, which tells us there are no, and I should actually be saying here, sorry, no real solutions. Okay. So let's just quickly run through these, and I think we are good to go from here. So if the graph of a linear equation and the graph of a system of quadratic equations intersect at 2 points, the linear equation system has 2 solutions. Yeah, because there's 2 intersections. If they intersect at 1 point, then the linear quadratic system has 1 solution, and of course there is no intersection at all, then there are 0 solutions. So if we solve the system, we end up solving a quadratic, and the discriminant obviously tells us the number of solutions and the nature of those solutions. If you recall, the nature of our roots, in this particular case, the solutions. So if there are two distinct roots, then the discriminant is going to be greater than 0, and the linear quadratic system has two solutions. If the equation has two equal roots, then the discriminant is equal to 0, and the linear quadratic system has one solution, and if there are no real roots, the discriminant is less than 0, and there are 0 solutions. Okay, so again, just because it does not factor, okay, then we can use the quadratic formula. It does not mean there are no solutions. Okay, and just as with circle geometry, we know that if there's only one point of intersection, then the line is tangent to the parabola. Okay, so please check for the assigned questions and let me know if you guys have any questions. Thank you.